We're about to embark on a journey that will stretch your mind to its absolute limits. A journey that will take us from the comfort of our small blue planet to the very edges of existence itself. Tonight, we're going to tackle one of the most mind-bending questions humanity has ever dared to ask. How many stars actually exist in this universe? Now, before we dive headfirst into this cosmic mystery, I'd love to know where you're listening from. Drop your location and time in the comments below. There's something beautifully poetic about people scattered across our tiny world, all looking up at the same infinite sky, all wondering about the same impossible question. Each of us is sitting under that same vast canopy of stars that has inspired countless generations before us. If you find yourself captivated by these gentle explorations of our cosmos, I'd be incredibly grateful if you'd consider subscribing and giving this video a like. It helps the algorithm find more curious souls like us who lie awake at night wondering about the deepest mysteries of existence. Your support helps me create these long-form journeys into the unknown, and honestly, it means the world to me. The visuals are here to guide you, but feel free to close your eyes, let your breathing slow, and allow your imagination to drift among the stars themselves. There's absolutely no pressure to stay awake through every word. Sometimes the most profound realizations come when we're floating on the edge between consciousness and dreams. So let's begin this impossible quest together. Picture yourself standing in the middle of an empty field on the darkest night you can imagine. No city lights, no moon, just you and the cosmos above. As your eyes adjust to the darkness, stars begin to emerge. First dozens, then hundreds, then thousands of pinpricks of light scattered across the black velvet of space. What you're seeing with your naked eyes is roughly 4,000 stars. 4,000 ancient suns, each one a blazing furnace of nuclear fire, some larger than our sun, some smaller, some dying, some being born at this very moment. 4,000 seems like an enormous number when you're lying on your back, neck craned toward infinity. But here's where our journey takes its first mind-bending turn. Those 4,000 stars you can see represent such an infinitesimally small fraction of reality that it's almost laughable. It's like trying to understand the ocean by examining a single drop of water under a microscope. Every single star you've ever seen with your naked eyes lives in our home galaxy, the Milky Way. And our Milky Way, that sprawling cosmic island we call home, contains somewhere between 200 billion and 400 billion stars. Let me say that again slowly. Our galaxy alone holds up to 400 billion stars. Think about that for a moment. 400 billion individual suns, each potentially warming their own collection of planets, each burning with the fury of nuclear fusion, each representing possibilities we can barely begin to imagine. And that's just our neighborhood in the cosmic sense. But we're not even getting started yet. Because our galaxy, magnificent as it is just one galaxy among an almost incomprehensible multitude. Recent observations suggest there are approximately 2 trillion galaxies scattered throughout the observable universe. 2 trillion separate cosmic islands, each containing billions or even trillions of their own stars. Now, I need you to pause here and really let this sink in. We're talking about 2 trillion galaxies, each potentially containing hundreds of billions of stars. The mathematics alone should make your head spin. But the reality behind those numbers is so staggering that human language starts to break down when we try to describe it. Astronomers have attempted to calculate the total number of stars in the observable universe, and their estimates range from mind-numbing to absolutely incomprehensible. The most conservative estimates suggest there are roughly 70 billion trillion stars out there. That's a 7 followed by 22 zeros. But more recent calculations push that number even higher, with some scientists suggesting we're looking at 200 sextillion stars. To put this in perspective, imagine every grain of sand on every beach on Earth, every tiny particle of quartz and shell and rock that makes up the shorelines of our entire planet. The number of stars in the universe likely exceeds even that astronomical count. You could gather every grain of sand from every beach, every desert, every sandbox, and you still might not have enough grains to represent every star burning in the cosmos. But here's where our story gets even more fascinating. These numbers we're throwing around represent only what we call the observable universe. This is the bubble of space around us from which light has had enough time to reach Earth since the Big Bang occurred roughly 13.8 billion years ago. The observable universe extends about 46.5 billion light-years in every direction from Earth. Beyond that boundary lies the great unknown. We have no idea how much more universe exists out there beyond our cosmic horizon. The actual universe could be infinitely large, containing infinitely more galaxies and infinitely more stars. Some cosmologists suggest that if certain models of cosmic inflation are correct, the total universe could contain more stars than we have ways to count. We're talking about numbers so large they require scientific notation with hundreds of digits. Numbers that make our earthly concepts of big seem absolutely trivial. Now, you might be wondering how astronomers even begin to estimate such impossible quantities. After all, we can't exactly send out cosmic census takers to count every star individually. The process is actually quite elegant in its simplicity, even if the execution requires some of the most sophisticated technology humanity has ever created. The fundamental approach works like this. Astronomers carefully study representative samples of the universe, measuring the number and types of galaxies in specific regions of space. They then extrapolate these measurements across the entire observable universe. It's similar to how pollsters might survey 1,000 people to predict how millions will vote, except astronomers are dealing with scales that dwarf human comprehension. But counting galaxies is only half the challenge. Each galaxy contains a vastly different number of stars depending on its type and size. Our Milky Way is actually considered a fairly large galaxy. Many galaxies are much smaller dwarf systems containing only a few million stars. Others are massive elliptical giants that can house over 1 trillion stellar inhabitants. This diversity makes the counting process incredibly complex. You can't simply multiply the number of galaxies by the number of stars in the Milky Way and expect an accurate answer. In fact, if you did that calculation, you'd overestimate the total stellar population by hundreds or even thousands of times, because the Milky Way is much larger than the average galaxy. The smallest galaxies, called dwarf ellipticals, are actually the most common type of galaxy in our local cosmic neighborhood. These tiny stellar cities might contain only 10 million stars each. Compare that to giant elliptical galaxies, the cosmic megalopolises that can contain over 1 trillion stars. The range is so enormous that creating accurate statistical models requires incredible precision and sophisticated mathematics. Recent advances in telescope technology have revolutionized our ability to peer deeper into space and count these distant stellar populations. The Hubble Space Telescope has allowed us to see galaxies so distant that we're observing them as they appeared when the universe was just a fraction of its current age. The newer James Webb Space Telescope has pushed these boundaries even further, revealing galaxies that formed when the cosmos was barely out of its infancy. These observations have revealed something remarkable about the early universe. Star formation in the cosmic past was actually much more vigorous than it is today. Billions of years ago, galaxies were churning out new stars at rates that dwarf current stellar birth rates. This means that many of the stars we're counting today are ancient citizens of the universe, some nearly as old as the cosmos itself. The oldest known star, nicknamed the Methuselah star, is estimated to be over 14 billion years old. This ancient sun has been burning since shortly after the Big Bang itself, a cosmic survivor that has witnessed the entire history of galactic evolution. When this star first ignited, the universe was a very different place, filled with only the simplest elements forged in the primordial fireball of creation. These ancient stars tell us something profound about the cosmic story we're trying to understand. In the beginning, the universe contained only hydrogen and helium, the simplest elements forged in those first moments after the Big Bang. But stars are cosmic alchemists, fusing lighter elements into heavier ones in their nuclear cores. When massive stars die in spectacular supernova explosions, they scatter these newly created elements throughout space, enriching the cosmic environment for future generations of stars. This means that different stellar populations carry the chemical fingerprints of their birth era. The oldest stars are metal poor, containing almost exclusively hydrogen and helium. Younger stars like our Sun are metal rich, incorporating the heavy elements created by countless previous generations of stellar death and rebirth. It's a beautiful cycle of cosmic recycling that has been playing out for nearly 14 billion years. The European Space Agency's Gaia mission has given us unprecedented insight into this stellar archaeology within our own galaxy. This remarkable spacecraft has precisely measured the positions, movements, and chemical compositions of nearly 2 billion stars in the Milky Way. Through this data, astronomers have discovered that our galaxy has a complex history of mergers and collisions with smaller galaxies, each event adding new stellar populations to our cosmic home. One particularly fascinating discovery from Gaia involves the identification of stars that originally formed in completely different galaxies. These stellar immigrants were incorporated into the Milky Way when their home galaxies collided with ours billions of years ago. By studying their unique chemical signatures, astronomers can trace the violent history of galactic cannibalism that has shaped our local corner of the universe. But as we zoom out from our galactic neighborhood to consider the universe as a whole, we encounter stellar environments that are almost unimaginably different from our own. In the dense cores of galaxy clusters, where hundreds of galaxies are packed together by gravity, stellar collisions are common events. Stars that have orbited peacefully for billions of years suddenly find themselves on collision courses, creating spectacular stellar explosions and exotic objects we're only beginning to understand. At the other extreme, in the vast voids between galaxy superclusters, space is so empty that individual galaxies drift in almost perfect isolation. These lonely island universes contain their stellar populations in cosmic solitude, with the nearest neighboring galaxy millions of light years away. The stars in these isolated galaxies experience a completely different cosmic environment, one where galactic interactions and stellar exchanges are virtually impossible. The distribution of stars throughout the universe follows patterns that reveal the underlying architecture of space itself. Galaxies aren't randomly scattered through the cosmos like stars in the night sky. Instead, they're organized into an intricate cosmic web of filaments and voids. Picture soap bubbles clustering together, with the galaxies concentrated along the thin films where the bubbles meet, while vast empty regions represent the interior spaces of the bubbles. This cosmic web structure profoundly influences where stars can form and how they evolve over time. In the dense filaments where galaxies cluster together, star formation proceeds at different rates than in the isolated void regions. The complex interplay of gravity, gas dynamics, and galactic interactions creates a universe where stellar populations vary dramatically depending on their cosmic address. When we try to count all these stars distributed throughout this vast cosmic web, we're essentially attempting to survey an entire universe of stellar cities, each with its own unique population and history. Some regions are experiencing vigorous star formation, birthing thousands of new stars every year. Others have exhausted their raw materials and contain primarily ancient stellar populations slowly fading away. The Carina Nebula provides a stunning example of active star formation that we can observe in detail. This stellar nursery, located about 7,500 light-years from Earth, is currently giving birth to massive stars at an incredible rate. The James Webb Space Telescope has revealed this region in unprecedented detail, showing us stellar embryos still cocooned within their birth clouds of gas and dust. What makes the Carina Nebula particularly remarkable is its scale of stellar production. The most massive stars forming within its boundaries will burn through their nuclear fuel in just a few million years before exploding as supernova. These stellar giants are so luminous that a single one can outshine entire smaller galaxies. Yet they represent just a tiny fraction of the stellar population we're trying to count across the entire universe. The famous Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, represents another active stellar manufacturing center. Located just over 1,300 light-years from Earth, this stellar nursery contains approximately 2,800 young stars in various stages of formation. Recent observations have even revealed pairs of free-floating gas giant planets forming within the nebula, demonstrating that planetary systems are an integral part of the star formation process. These stellar nurseries are scattered throughout every galaxy in the universe, each contributing to the ongoing cosmic census of stars. But star formation isn't a steady, constant process. It varies dramatically based on the availability of raw materials, the local gravitational environment, and the influence of nearby massive stars. Some galaxies are experiencing intense bursts of star formation, creating thousands of new stars per year. Others have become quiescent, forming only a handful of new stars per century. The challenge of counting stars becomes even more complex when we consider that stellar populations are constantly changing. Every second, new stars are being born while others are dying. Massive stars live fast and die young, exploding as supernovae after just a few million years. Smaller stars like our Sun burn their nuclear fuel more conservatively, potentially shining for tens of billions of years. Red dwarf stars, the smallest and most common type of star, can burn for trillions of years. This means that virtually every red dwarf that has ever formed is still shining today, since the universe hasn't existed long enough for any of them to die of old age. These tiny stellar survivors will continue burning long after our sun has exhausted its fuel and faded away. The death of massive stars adds another layer of complexity to our cosmic census. When these stellar giants explode, they don't simply vanish. Instead, they leave behind exotic remnants like neutron stars and black holes. Neutron stars are so dense that a single teaspoon of their material would weigh as much as Mount Everest. Black holes represent regions of space where gravity has become so intense that not even light can escape. These stellar remnants still count as part of the cosmic stellar population, even though they no longer shine with nuclear fire. In fact, our galaxy likely contains millions of these dark stellar corpses, invisible to our telescopes, but still influencing the gravitational dance of nearby objects. When astronomers attempt to count the total stellar population of the universe, they must somehow account for these hidden populations of stellar ghosts. Binary and multiple star systems add yet another complication to our counting efforts. Recent surveys suggest that most stars don't exist in isolation like our Sun, but instead are born as part of complex gravitational partnerships. Some systems contain two stars orbiting each other, while others host 3, 4, or even more stellar companions locked in intricate orbital dances. The Gaia mission has identified hundreds of thousands of these multiple star systems within our galaxy alone. Some are so close together that they actually share material, with gas streaming from one star to its companion in spectacular stellar displays. Others are separated by distances larger than the orbit of Pluto, making their gravitational connection almost imperceptible. When we scale these discoveries up to the entire observable universe, we begin to appreciate just how complex the task of stellar census taking really becomes. We're not just counting individual points of light, but rather attempting to survey an incredibly diverse ecosystem of stellar objects, each with its own unique properties, life cycle, and cosmic environment. The numbers we derive from these surveys represent our best current understanding of the stellar universe, but they come with enormous uncertainties. Every estimate depends on assumptions about galaxy types, stellar populations, and cosmic evolution that are still being refined by ongoing observations. As our telescopes become more powerful and our theoretical models more sophisticated, these numbers will undoubtedly continue to evolve. What remains constant, however, is the absolutely staggering scale of the cosmic stellar population. Whether we settle on 70 billion trillion stars or 200 sextillion, we're dealing with numbers that challenge the very limits of human comprehension. These aren't just abstract mathematical concepts, but represent real physical objects burning throughout the cosmos, each one a potential sun for worlds we can barely imagine. As you drift deeper into contemplation of these cosmic scales, remember that you're connected to this vast stellar community in the most intimate way possible. Every atom in your body, except for hydrogen, was forged in the nuclear furnace of a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created by stellar alchemy and scattered into space by dying stars. You are, quite literally, made of star stuff. And as you rest here tonight, pondering the impossible vastness of the stellar universe, you're participating in the cosmos' attempt to understand itself. Through your curiosity, through your wonder, the universe is contemplating its own magnificent complexity. The stars you can see twinkling outside your window are just the tiniest sample of a stellar population so vast that it defies all earthly comparison. Yet each one burns with the same nuclear processes, follows the same physical laws, and participates in the same cosmic dance of gravity and light that has been unfolding for nearly 14 billion years. 14 billion years. The story of stellar formation reveals itself as one of the most elegant processes in the entire cosmos. When we peer into stellar nurseries like the Eagle Nebula or the Rosette Nebula, we witness creation itself unfolding in slow motion across millions of years. These regions begin as vast molecular clouds, collections of gas and dust so cold they approach absolute zero, drifting through space like cosmic snowflakes waiting for the right gravitational nudge. Something triggers the collapse, perhaps the shockwave from a nearby supernova or the gravitational influence of a passing star. Whatever the catalyst, these frigid clouds begin to contract under their own gravity. As they shrink, they fragment into smaller clumps, each destined to become a stellar nursery. Within these fragments, dense cores form, where temperatures and pressures climb steadily toward the critical threshold for nuclear ignition. The birth of a star is not a gentle process. As gravitational collapse accelerates, the core temperature soars to millions of degrees. Hydrogen atoms, stripped of their electrons by the intense heat, begin slamming into each other with enough force to overcome their natural electromagnetic repulsion. When 4 hydrogen nuclei finally fuse to create a single helium nucleus, a star is truly born, beginning its long journey through the cosmic night. But stellar birth rates vary dramatically throughout the universe, creating a complex tapestry of stellar ages and populations. In some regions, star formation proceeds at a leisurely pace, with new stars appearing perhaps once every few centuries. In others, stellar nurseries are so active that dozens of massive stars ignite simultaneously, creating spectacular stellar associations that can outshine entire galaxies for brief periods. The antennae galaxies provide a stunning example of what happens when star formation goes into overdrive. These 2 spiral galaxies are in the process of colliding, and their gravitational interaction has triggered one of the most intense bursts of star formation ever observed. Within the collision zone, new stars are being born at a rate nearly 100 times faster than in our own Milky Way. When we multiply these varying star formation rates across 2 trillion galaxies, each with its own unique history and environment, the complexity of our cosmic census becomes almost overwhelming. Some galaxies exhausted their star-forming material billions of years ago and now contain only ancient stellar populations slowly fading away. Others are still in their stellar prime, actively converting gas into new generations of stars. Elliptical galaxies represent the retirement communities of the cosmic stellar population. These massive, roughly spherical collections of stars typically formed most of their stellar inhabitants in intense bursts billions of years ago. Today, they contain primarily old, red stars, slowly consuming their remaining nuclear fuel. The lack of ongoing star formation gives these galaxies a characteristic golden glow, the combined light of countless aging suns. Spiral galaxies like our Milky Way tell a different story entirely. Their graceful spiral arms trace ongoing waves of star formation, marking regions where gas clouds are being compressed and triggered to collapse. The blue light from young, massive stars illuminates these spiral patterns, creating some of the most beautiful structures in the entire universe. Each spiral arm represents a stellar construction zone where new stars are constantly being added to the galactic population. Irregular galaxies defy easy categorization, often bearing the scars of gravitational interactions or merger events. The large and small Magellanic Clouds, satellite galaxies of our own Milky Way, show clear evidence of tidal disruption from their larger neighbor. Their distorted shapes and active star formation regions tell the story of gravitational forces reshaping stellar populations across cosmic time. The diversity of galactic environments creates an equally diverse range of stellar populations. In the dense central regions of massive galaxies, stars are packed so closely together that close encounters and even stellar collisions become relatively common. These crowded stellar neighborhoods produce exotic objects like blue straggler stars, which appear younger than they should be due to mass transfer from nearby companions. At the opposite extreme, stars in the outer regions of galaxies or in dwarf galaxies experience a much more isolated existence. These stellar hermits may go billions of years without experiencing significant gravitational influences from their neighbors. Their evolution proceeds according to their initial mass and composition, undisturbed by the complex interactions that shape stellar populations in denser environments. Recent discoveries have revealed that many galaxies contain multiple distinct stellar populations with different ages and chemical compositions. These discoveries suggest that galaxy formation was not a single event, but rather an ongoing process of accretion and merger spanning billions of years. Each merger event added new stellar populations to the growing galactic collection, creating the complex mix of stellar ages and compositions we observe today. The chemical evolution of stellar populations provides another fascinating dimension to our cosmic story. The very first stars that formed after the Big Bang contained only hydrogen and helium, the primordial elements forged in the cosmic fireball. These population 3 stars, as astronomers call them, were likely much more massive than typical stars today, burning brilliantly but briefly before exploding and scattering the first heavy elements into space. Successive generations of stars incorporated these heavy elements into their composition, gradually enriching the cosmic environment. Each stellar generation built upon the nuclear achievements of its predecessors, creating an ever more complex chemical inventory. Stars forming today have access to the full periodic table of elements, enabling the formation of rocky planets and the complex chemistry necessary for life. This chemical enrichment process continues today throughout the universe, but at vastly different rates in different environments. Galaxies with active star formation are still rapidly processing gas into stars and heavy elements. Quiescent galaxies have largely completed their chemical evolution, containing stellar populations with relatively uniform compositions reflecting their ancient formation epochs. The role of supermassive black holes adds another layer of complexity to stellar population dynamics. Nearly every galaxy harbors a supermassive black hole at its center, containing millions or billions of solar masses compressed into a region smaller than our solar system. When material falls into these cosmic monsters, it releases enormous amounts of energy that can influence star formation throughout the entire galaxy. Active galactic nuclei powered by accretion onto central black holes, can generate winds and jets energetic enough to blow gas completely out of their host galaxies. This process, called feedback, can effectively shut down star formation by removing the raw materials needed to create new stars. The interplay between black hole activity and stellar populations represents one of the most active areas of current astronomical research. Galaxy clusters, the largest gravitationally bound structures in the universe, create yet another set of environmental influences on stellar populations. Within these massive collections of hundreds or thousands of galaxies, gravitational interactions become much more frequent and intense. Galaxies can be stripped of their gas by high-speed encounters with the hot intracluster medium, effectively ending their star formation careers. The phenomenon of galaxy harassment occurs when smaller galaxies repeatedly pass close to more massive neighbors within a cluster environment. Each close encounter strips away some of the smaller galaxies' stars and gas, gradually transforming spiral galaxies into smaller, more compact, elliptical systems. This process contributes significantly to the evolution of stellar populations in dense environments. Gravitational lensing by galaxy clusters provides astronomers with a powerful tool for studying distant stellar populations that would otherwise be too faint to observe. The immense gravity of a cluster can magnify and brighten background galaxies, effectively turning the cluster into a cosmic telescope. This natural magnification has allowed astronomers to study stellar populations in some of the most distant galaxies ever observed. The cosmic web itself influences stellar populations on the largest scales imaginable. Galaxies located along the dense filaments of the web experience different evolutionary pressures than those residing in the vast cosmic voids. Filament galaxies have access to steady streams of fresh gas flowing along the cosmic web, potentially extending their star formation careers. Void galaxies, in contrast, must rely primarily on their initial gas reservoirs. Studies of stellar populations in different cosmic environments reveal systematic differences that reflect these large-scale influences. Void galaxies tend to be bluer and more actively star-forming than their counterparts in denser regions, suggesting that environmental quenching processes are less effective in the cosmic wilderness. These observations help astronomers understand how the large-scale structure of the universe shapes the detailed properties of individual stellar populations. The discovery of ultra-diffuse galaxies has challenged traditional notions of stellar population density and galaxy formation. These ghostly systems contain roughly the same number of stars as typical dwarf galaxies, but spread over areas comparable to much larger systems, like the Milky Way. Their existence suggests that stellar populations can be distributed in ways that defy conventional expectations about galaxy structure. Some ultra-diffuse galaxies appear to contain unusually large numbers of globular clusters, dense spherical collections of ancient stars that typically orbit larger galaxies. The presence of these stellar fossils in such diffuse systems provides clues about their formation history and suggests that they may be the remnants of more massive galaxies that have been tidally disrupted by their environment. The study of globular clusters themselves reveals fascinating details about ancient stellar populations. These systems, which can contain hundreds of thousands to millions of stars packed into spherical regions, just tens of light years across, represent some of the oldest stellar populations in the universe. Their stars formed when the cosmos was young, and the chemical environment was much simpler than it is today. Recent observations have revealed that many globular clusters contain multiple stellar populations with subtly different chemical compositions. This discovery suggests that these systems experienced multiple episodes of star formation, challenging earlier assumptions about their formation as single-age stellar populations. The complex internal structure of globular clusters provides a microcosm for understanding stellar population evolution on larger scales. Stellar streams represent another fascinating aspect of galactic stellar populations. These elongated structures form when smaller stellar systems are tidally disrupted by the gravity of larger galaxies. The Sagittarius stream, which wraps around our Milky Way multiple times, represents the remnants of a dwarf galaxy that is slowly being torn apart by our galaxy's gravitational field. The detection and study of stellar streams has revolutionized our understanding of galactic assembly and stellar population mixing. Each stream carries the chemical fingerprint of its parent system, allowing astronomers to trace the merger history of galaxies and understand how stellar populations from different sources have been combined over cosmic time. Hypervelocity stars represent some of the most extreme members of galactic stellar populations. These stellar speed demons have been ejected from their parent galaxies at velocities exceeding the galactic escape speed, condemning them to wander through intergalactic space for eternity. Most hypervelocity stars are thought to originate from close encounters with the supermassive black holes at galactic centers, which can gravitationally slingshot stars to incredible velocities. The existence of hypervelocity stars adds another dimension to stellar population counts, as these objects represent stars that have been permanently removed from their parent galaxies. Over cosmic time, this process gradually depletes galactic stellar populations while contributing to a diffuse intergalactic stellar component that is extremely difficult to observe and quantify. Intracluster light, the faint glow of stars that have been stripped from galaxies within galaxy clusters, represents another hidden component of the cosmic stellar population. These orphaned stars, liberated from their parent galaxies by gravitational interactions, create a diffuse stellar envelope around entire galaxy clusters. Recent estimates suggest that this intracluster stellar component could account for a significant fraction of the total stellar mass in some clusters. The challenge of accounting for all these diverse stellar populations and environments when attempting to count the total number of stars in the universe becomes almost overwhelming. Every observational technique has its limitations and selection effects. Ground-based telescopes are limited by atmospheric interference. Space telescopes, while providing clearer views, have restricted fields of view and limited observing time. The cosmic distance ladder, the series of techniques astronomers use to measure distances to increasingly remote objects, introduces uncertainties that propagate through every stellar population estimate. A small error in distance measurement can translate into large uncertainties in stellar counts, especially when extrapolated across cosmic scales. Dust extinction further complicates stellar population studies by preferentially obscuring certain types of stars and entire regions of galaxies. Young, hot stars produce most of their light at blue and ultraviolet wavelengths that are easily absorbed by cosmic dust. This means that active star-forming regions, which should contribute significantly to stellar counts, can appear deceptively faint or even completely invisible at optical wavelengths. Infrared astronomy has partially solved this problem by allowing astronomers to peer through dusty regions and observe the thermal emission from dust grains heated by embedded stars. The Spitzer and Herschel space telescopes revolutionized our understanding of obscured stellar populations, revealing vast numbers of stars that had been hidden from optical surveys. The advent of large-scale survey telescopes has transformed stellar population studies by providing statistically robust samples of galaxies across cosmic time. Projects like the Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Legacy Survey of Space and Time promise to catalogue billions of galaxies and provide unprecedented insights into stellar population evolution. Machine learning and artificial intelligence are increasingly being applied to these massive data sets, allowing astronomers to identify subtle patterns and correlations that would be impossible to detect through traditional analysis methods. These computational approaches are revealing new classes of galaxies and stellar populations that challenge existing theoretical frameworks. The James Webb Space Telescope is pushing the boundaries of stellar population studies to even greater extremes, observing galaxies as they appeared when the universe was less than 1 billion years old. These observations are revealing that stellar populations in the early universe may have been fundamentally different from anything we see locally, with implications for understanding the full cosmic stellar census. As we continue to refine our understanding of stellar populations across all these diverse environments and evolutionary stages, the total count of stars in the universe remains a moving target. Each new discovery reveals additional complexity and nuance that must be incorporated into our cosmic accounting. The numbers we cite today will undoubtedly be revised as our observational capabilities and theoretical understanding continue to advance. What remains constant, however, is the absolutely breathtaking scale of the stellar universe and our profound connection to this cosmic stellar community. As you rest here tonight, contemplating these vast stellar populations scattered throughout space and time, remember that you carry within yourself the nuclear heritage of countless generations of stars that lived, died, and enriched the cosmos with their sacrifice. The story becomes even more extraordinary when we consider that stellar populations are not evenly distributed throughout the universe. Instead, they follow the intricate patterns of the cosmic web, creating a three-dimensional tapestry of stellar density that varies dramatically from one region to another. In the densest nodes where galaxy clusters congregate, stellar populations can be packed thousands of times more densely than in the vast cosmic voids that separate these islands of matter. Within the cosmic voids themselves, a different kind of stellar story unfolds. These regions, which can span hundreds of millions of light years with almost nothing inside them, contain isolated galaxies that have evolved in cosmic solitude. These lonely stellar systems have experienced a fundamentally different evolutionary path, with their stellar populations shaped primarily by internal processes rather than the complex environmental influences that affect galaxies in denser regions. Recent deep field observations have revealed that even these apparently empty voids are not completely devoid of stars. Faint streams of ancient starlight have been detected stretching across these cosmic deserts, suggesting the presence of extremely low-density stellar populations that may have been ejected from galaxies billions of years ago. These intergalactic wanderers represent yet another hidden component of the cosmic stellar census that we're only beginning to understand. The temporal dimension of stellar populations adds another layer of complexity to our counting efforts. When we observe distant galaxies, we're seeing them as they existed billions of years ago, when the universe was younger and stellar formation processes operated under very different conditions. The galaxies we observe at great distances may have evolved dramatically since the light we're receiving first began its journey toward Earth. This light travel time effect means that our census of distant stellar populations is actually a census of the ancient universe. The most distant galaxies visible to our most powerful telescopes show us stellar populations as they existed when the universe was less than 1 billion years old. These primordial stellar systems were forming their first generations of stars in an environment radically different from the universe we observe locally today. The early universe was smaller, denser, and hotter than it is now. Gas clouds that would eventually become galaxies were being compressed by the overall cosmic expansion and by the gravitational collapse of dark matter structures. Star formation rates in these early epochs were often dramatically higher than anything we observe in the local universe, leading to brief but incredibly intense periods of stellar birth. Some of these ancient stellar populations were so massive and luminous that individual galaxies could outshine entire modern galaxy clusters. The most massive stars formed during these early epochs were true stellar giants, containing hundreds of times more mass than our Sun, and burning through their nuclear fuel in just a few million years before exploding in supernova so powerful they could influence star formation across entire galactic regions. These ancient stellar explosions played a crucial role in dispersing heavy elements throughout the early universe, enriching the cosmic environment, and enabling the formation of more chemically complex stellar populations. Each successive generation of stars incorporated more heavy elements, gradually building up the chemical complexity that would eventually enable the formation of rocky planets and the organic chemistry necessary for life. The metallicity gradient we observe in stellar populations reflects this ongoing process of chemical enrichment. The oldest stellar populations, formed when the universe contained only hydrogen and helium, have chemical compositions that are remarkably uniform regardless of where we observe them. Younger stellar populations show much greater chemical diversity, reflecting the complex history of stellar nucleosynthesis and mixing processes that have operated over billions of years. Stellar archaeology, the study of chemical compositions in ancient stars, has revealed that our galaxy has experienced multiple distinct episodes of chemical enrichment. Each episode corresponds to different phases of galactic assembly, when smaller stellar systems were accreted and their chemical signatures mixed with the existing galactic population. This process continues today as the Milky Way slowly cannibalizes nearby dwarf galaxies. The Sagittarius dwarf galaxy, currently in the process of being torn apart by the Milky Way's gravity, is contributing its stellar population to our galaxy's census in real time. Streams of stars from this disrupted system can be traced wrapping around our galaxy multiple times, creating spectacular stellar rivers that will eventually merge completely with the Milky Way's population. Similar accretion processes are occurring throughout the universe, with larger galaxies continuously growing by consuming smaller stellar systems. This hierarchical assembly process means that the stellar populations we observe today are the products of countless merger and accretion events spanning cosmic history. Each galaxy's stellar census reflects not just its own star formation history, but also the accumulated stellar populations of all the systems it has absorbed over time. The discovery of ultra-compact dwarf galaxies has revealed stellar populations compressed to extraordinary densities. These systems, which contain millions of stars packed into regions just a few hundred light-years across, may represent the cores of larger galaxies that have been stripped of their outer stellar populations by gravitational interactions. Their extreme stellar densities create environments unlike anything found in normal galaxies. Within these ultra-compact systems, stellar interactions become much more frequent and dramatic. Close encounters between stars can alter their evolutionary paths, while stellar collisions can create exotic objects not found in less dense environments. These processes add complexity to stellar population models and demonstrate how environmental factors can dramatically influence the evolution of stellar systems. Brown dwarf stars represent another challenging component of stellar population counts. These failed stars, with masses too low to sustain hydrogen fusion in their cores, blur the boundary between stars and planets. Recent surveys suggest that brown dwarfs may be much more numerous than previously thought, potentially adding billions of these dim objects to galactic stellar censuses. The challenge of detecting and counting brown dwarfs illustrates the selection effects that plague all stellar population studies. These objects are so faint that they can only be detected in our immediate cosmic neighborhood, making it extremely difficult to estimate their contribution to the total cosmic stellar population. Similar detection biases affect our ability to count other types of faint stars, potentially leading to significant underestimates of total stellar numbers. Red dwarf stars, while much more luminous than brown dwarfs, are still so faint that they can only be individually detected in nearby galaxies. Yet these stars are thought to represent the most numerous stellar population in the universe, potentially accounting for 3/4 of all stars ever formed. The inability to directly count red dwarfs in distant galaxies introduces enormous uncertainties into cosmic stellar censuses. Statistical methods must be employed to estimate red dwarf populations based on observations of brighter, more easily detected stars. These techniques rely on assumptions about stellar mass functions and formation processes that may not apply universally across different galactic environments and cosmic epochs. Small changes in these assumptions can lead to order of magnitude differences in estimated stellar populations. The initial mass function, which describes the relative numbers of stars formed with different masses, is one of the most critical parameters in stellar population modeling. Observations within our local galactic neighborhood suggest a relatively universal relationship, with low-mass stars being much more numerous than high-mass stars. However, recent observations of distant galaxies hint that this relationship may vary significantly in different environments and epochs. If the initial mass function was systematically different in the early universe, when most stars were forming under very different physical conditions, then our estimates of the total stellar population could be dramatically incorrect. The possibility that stellar formation processes have evolved over cosmic time adds yet another layer of uncertainty to our cosmic census efforts. Stellar remnants represent a largely invisible component of the cosmic stellar population that must be accounted for in any complete census. White dwarf stars, neutron stars, and stellar mass black holes are the final endpoints of stellar evolution, but they contribute very little light compared to their progenitor stars. Yet these objects contain significant amounts of mass and represent the accumulated stellar death toll over cosmic history. The number of stellar remnants in a galaxy depends on its complete star formation history and the detailed physics of stellar evolution. Massive stars that formed billions of years ago have long since exploded and left behind neutron stars or black holes. Lower mass stars are still burning today, but will eventually evolve into white dwarf stars. The most numerous red dwarf stars will continue burning for trillions of years, meaning that virtually every red dwarf ever formed is still active today. This temporal evolution of stellar populations means that the cosmic stellar census is constantly changing. Every second, new stars are being born while others are dying. The rate of stellar birth has generally declined over cosmic history as galaxies have consumed their gas reservoirs and star formation has become less efficient. Meanwhile, the stellar death rate continues to increase as more and more stars reach the ends of their evolutionary lifespans. Gamma-ray bursts, among the most energetic events in the universe, mark the deaths of some of the most massive stars ever formed. These cosmic explosions can briefly outshine entire galaxies and are detectable across billions of light years. Each gamma-ray burst represents the transformation of a massive star into a black hole, removing one active star from the cosmic census while adding to the population of stellar remnants. The study of gamma-ray burst host galaxies has revealed that these extreme stellar deaths preferentially occur in small, metal-poor galaxies with active star formation. This observation suggests that the most massive stars, which produce gamma-ray bursts, form more readily in chemically primitive environments, similar to those that existed in the early universe when such stars were much more common. Pair instability supernovae represent an even more extreme form of stellar death that may have been common in the primordial universe. These catastrophic explosions completely destroy their progenitor stars, leaving behind no stellar remnant and dispersing all of the star's nuclear products into the surrounding medium. The existence of these events in the early universe could significantly affect estimates of primordial stellar populations and chemical enrichment rates. Population 3 stars, the very first generation of stars formed after the Big Bang, likely experienced these types of complete destruction events. These primordial giants, formed from gas containing only hydrogen and helium, may have been much more massive than typical stars today. Their explosive deaths would have enriched the early universe with the first heavy elements, enabling the formation of the more familiar stellar populations we observe today. The search for surviving population 3 stars represents one of the holy grails of stellar archaeology. Despite extensive surveys, no definitive examples of these primordial objects have been identified. This absence suggests that either these stars were too massive to survive until today, or that they are so rare and faint that they have escaped detection in current surveys. Theoretical models predict that population 3 stars should have been extremely massive, perhaps containing hundreds of solar masses. Such giants would have burned through their nuclear fuel in just a few million years before exploding in hypernova events that completely destroyed the star. If these models are correct, then none of the universe's first stars survive today, existing only as the heavy elements they scattered throughout space. The chemical signatures of population 3 stellar deaths can still be detected in some of the oldest surviving stars. These ancient stellar fossils contain trace amounts of heavy elements that could only have been produced by the nuclear processes operating in primordial stellar cores. By studying these chemical fingerprints, astronomers can infer properties of stellar populations that existed over 13 billion years ago. Globular clusters provide another window into ancient stellar populations and their contribution to cosmic stellar censuses. These dense stellar systems, containing hundreds of thousands to millions of stars, represent some of the oldest organized stellar populations in the universe. Their stars formed when galaxies were young, and their chemical compositions preserve records of early stellar nucleosynthesis processes. Recent observations have revealed that many globular clusters contain multiple stellar populations with different ages and chemical compositions. This discovery suggests that these systems experienced extended periods of star formation, rather than forming all their stars in a single burst. The existence of multiple populations within globular clusters complicates both their formation models and their contribution to overall galactic stellar censuses. The total mass contained in globular cluster systems provides another approach to estimating stellar populations in distant galaxies where individual stars cannot be resolved. The relationship between globular cluster populations and total galactic stellar mass has been calibrated using nearby galaxies, allowing astronomers to estimate stellar populations in much more distant systems based on their globular cluster content. Planetary nebulae represent another tracer of stellar populations, particularly intermediate mass stars in the final stages of their evolution. These beautiful shells of glowing gas, expelled by dying stars, can be detected in galaxies far too distant for individual stellar observations. The number and properties of planetary nebulae in a galaxy provide information about its stellar population age and star formation history. The relationship between planetary nebula populations and total stellar mass varies depending on the age and chemical composition of the underlying stellar population. Young stellar populations contain many intermediate mass stars that will eventually produce planetary nebulae, while older populations may have already exhausted this stellar mass range. These evolutionary effects must be carefully modeled when using planetary nebulae as stellar population tracers. Supernova rates provide yet another method for estimating stellar populations and star formation histories in distant galaxies. Type Ia supernovae, produced by exploding white dwarf stars, occur at rates proportional to the total stellar mass in old stellar populations. Type II supernovae, produced by massive star explosions, trace current star formation rates and young stellar populations. The combination of different supernova types allows astronomers to probe both young and old stellar populations in the same galaxy, providing constraints on total stellar mass and star formation history. Large supernova surveys have detected thousands of these stellar explosions in galaxies across cosmic time, building statistical samples that inform stellar population models. Variable star populations offer another approach to stellar census work, particularly for intermediate distance galaxies, where individual bright stars can still be resolved. Cepheid variable stars, with their well-calibrated period luminosity relationships, serve as both distance indicators and tracers of young stellar populations. RR Lyrae variables similarly trace old stellar populations and can be detected in the outer regions of nearby galaxies. The discovery of intermediate luminosity optical transients has revealed a new class of stellar events that may significantly affect stellar population counts. These events, which are less energetic than supernovae, but much more luminous than nova explosions, may represent a previously unrecognized mode of stellar death or evolution, Their contribution to stellar population dynamics is still being investigated. Tidal disruption events, caused when stars venture too close to supermassive black holes, provide dramatic demonstrations of how galactic environments can affect stellar populations. These events, which produce bright flares as stars are torn apart and consumed, occur at rates that depend on both the central black hole mass and the density of the surrounding stellar population. The study of tidal disruption event rates in different types of galaxies provides information about both central black hole masses and nuclear stellar population densities. These observations help constrain models of galactic evolution and the co-evolution of black holes and their host stellar systems. Gravitational wave detections of merging stellar mass black holes have opened an entirely new window into stellar populations and their evolution. These events trace the final stages of massive binary star evolution and provide information about stellar populations that formed billions of years ago. The rates and properties of gravitational wave sources constrain models of stellar evolution and binary formation processes. The diversity of gravitational wave sources detected so far suggests that stellar populations contain a rich variety of compact object binaries formed through different evolutionary pathways. Some systems may have formed through isolated binary evolution, while others may have been assembled through dynamical interactions in dense stellar environments like globular clusters. As we contemplate these myriad approaches to understanding and counting stellar populations throughout the universe, the true complexity of the cosmic stellar census becomes apparent. Every method has its strengths and limitations, its selection effects, and systematic uncertainties. The challenge lies not just in making individual measurements, but in combining these diverse observational approaches into a coherent picture of the total stellar population. The numbers we derive from this painstaking process of cosmic accounting represent humanity's best current estimate of one of the most fundamental questions about our universe. Whether the final count settles on tens of sextillions or hundreds of sextillions of stars, we are confronting a scale that transcends ordinary human experience and challenges our ability to find meaning in such vastness. Yet perhaps the most remarkable aspect of this cosmic stellar census is not the final number itself, but the fact that conscious beings like ourselves have evolved from stellar processes to contemplate their own cosmic origins. Every atom in your body was forged in stellar cores and scattered by stellar explosions, making you a living library of stellar nucleosynthesis stretching back through cosmic history. As you rest here tonight, breathing slowly and letting your mind drift among these countless stellar populations, remember that you are not separate from this vast cosmic story. You are an active participant in the universe's ongoing evolution, a temporary but magnificent arrangement of stellar materials that has achieved the extraordinary feat of self-awareness and cosmic contemplation. The stars scattered throughout those 2 trillion galaxies continue their ancient dance of birth, life and death, creating the elements and energy that make complexity and consciousness possible. Through your wonder, through your questions, through your very existence, the universe has found a way to know itself, to count its own stellar citizens, and to marvel at the improbable beauty of its own vast and intricate design. The stellar formation processes we observe today represent just the latest chapter in a cosmic story that has been unfolding for nearly 14 billion years. Within the dense cores of molecular clouds, where temperatures hover just above absolute zero, gravity slowly but inexorably pulls matter together into ever denser concentrations. These stellar nurseries operate on timescales that dwarf human experience, with the birth of a single star requiring millions of years from initial collapse to nuclear ignition. What makes this process even more remarkable is its incredible efficiency in converting raw cosmic materials into the fundamental building blocks of complexity. When a protostar finally achieves the critical temperature and pressure needed for nuclear fusion, it joins a cosmic community that has been growing steadily since the first stars ignited in the primordial darkness over 13 billion years ago. The diversity of stellar types emerging from these formation processes adds yet another layer of complexity to our cosmic census. Each molecular cloud gives birth to a mixed stellar population, with the most massive stars burning brilliantly but briefly, while the smallest red dwarfs settle in for trillion-year lifespans that will outlast countless generations of their more massive siblings. This temporal diversity means that the stellar population we observe at any given moment represents a complex mixture of different stellar generations. Ancient red dwarfs that formed when the universe was young continue burning alongside stars born just yesterday in cosmic terms. The interplay between these different stellar populations creates the rich tapestry of galactic evolution we observe throughout the universe. Binary star formation adds another dimension to this already complex picture. Recent observations suggest that most stars are born not in isolation, but as part of gravitationally bound multiple systems. These stellar partnerships can profoundly influence each star's evolutionary path, with mass transfer between companions creating exotic objects that would be impossible in single star systems. Some binary systems are so close that their stellar surfaces almost touch, creating spectacular displays as material streams from one star to its companion. Others are separated by distances comparable to entire solar systems, with orbital periods measured in thousands of years. The gravitational dance between these stellar partners can persist for billions of years, gradually altering both stars through tidal interactions and mass exchange. When we scale these complex stellar formation and evolution processes up to galactic dimensions, the sheer scope of the cosmic stellar census becomes almost overwhelming. Each galaxy represents a stellar ecosystem containing billions or trillions of individual stars, each following its own evolutionary trajectory, while participating in the larger gravitational choreography of galactic dynamics. The spiral arms of disk galaxies trace ongoing waves of stellar formation, marking regions where density waves compress the interstellar medium and trigger new episodes of stellar birth. These spiral patterns persist for billions of years, continuously recycling galactic gas into successive generations of stars, while gradually enriching the cosmic environment with heavy elements produced by stellar nuclear synthesis. Elliptical galaxies tell a different story of stellar population evolution. These massive, roughly spherical systems typically formed most of their stars in intense bursts during the early universe, when galaxy mergers were more common and gas densities were higher. Today, they contain primarily old stellar populations slowly consuming their remaining nuclear fuel, creating the characteristic golden glow that distinguishes them from actively star-forming spiral systems. The environmental factors affecting stellar populations extend far beyond individual galaxies to encompass the large-scale structure of the universe itself. Galaxy clusters, containing hundreds or thousands of individual galaxies bound together by gravity, create unique environments where stellar populations evolve under extreme conditions rarely found in isolated systems. Within these dense galactic congregations, high-speed encounters between galaxies can strip away gas and disrupt stellar formation processes. The hot intracluster medium, heated to millions of degrees by gravitational compression, can sweep gas away from galaxies through ram pressure stripping, effectively ending their star formation careers and freezing their stellar populations in time. Conversely, galaxies residing in the vast cosmic voids experience a fundamentally different evolutionary environment. These isolated systems, separated from their nearest neighbors by hundreds of millions of light-years, must rely primarily on their internal gas reservoirs for continued star formation. Their stellar populations evolve in cosmic solitude, largely unaffected by the environmental processes that shape galaxies in denser regions. Recent deep surveys have revealed that even these apparently empty void regions contain faint stellar populations that challenge our understanding of galactic evolution. Streams of ancient starlight have been detected stretching across cosmic voids, suggesting the presence of extremely diffuse stellar halos, or populations of intergalactic stars ejected from their parent galaxies billions of years ago. These discoveries highlight the dynamic nature of stellar populations over cosmic time. Galaxies are not static collections of stars, but rather evolving systems that continuously exchange material with their environments. Stellar streams, tidal tails, and diffuse halos all represent evidence of ongoing gravitational interactions that redistribute stellar populations throughout the cosmic web. The chemical evolution of stellar populations provides another powerful tool for understanding their formation and evolution over cosmic time. Each generation of stars inherits the nuclear legacy of previous stellar generations, gradually building up the chemical complexity that enables the formation of rocky planets and organic molecules. This process of cosmic chemical enrichment has been ongoing since the first massive stars exploded as supernovae over 13 billion years ago. Each stellar explosion scattered newly synthesized heavy elements into the surrounding interstellar medium, where they could be incorporated into subsequent generations of stars and planetary systems. The metallicity gradients observed in stellar populations reflect this ongoing process of chemical enrichment. Stars forming in the central regions of galaxies, where gas densities are higher and stellar formation rates more intense, typically show higher heavy element abundances than stars forming in the outer galactic regions, where chemical enrichment has proceeded more slowly. Stellar archaeology, the study of chemical compositions in ancient stars, has revealed that our own galaxy has experienced multiple distinct episodes of chemical enrichment corresponding to different phases of galactic assembly. Each episode reflects the merger or accretion of smaller stellar systems, each contributing their own unique chemical signatures to the growing galactic population. The most metal-poor stars observable today provide direct windows into the earliest epochs of stellar formation, when the universe contained only the primordial elements produced in Big Bang nucleosynthesis. These stellar fossils carry chemical fingerprints of the very first stars, allowing astronomers to infer properties of stellar populations that ceased to exist over 10 billion years ago. Population synthesis models attempt to combine all these diverse aspects of stellar formation, evolution, and chemical enrichment into comprehensive frameworks for understanding how stellar populations evolve over cosmic time. These sophisticated computer simulations track the birth, evolution, and death of billions of individual stars within realistic galactic environments. The complexity of these models reflects the intricate interplay between stellar physics, galactic dynamics, and cosmological evolution that shapes observable stellar populations. Each model must account for the initial mass function of newly formed stars, the detailed physics of stellar evolution, the chemical yields of different types of stellar explosions, and the environmental factors that influence star formation rates. Validation of these population synthesis models requires comparison with observations spanning a wide range of cosmic environments and evolutionary stages. The most distant galaxies observable with current telescopes provide snapshots of stellar populations as they existed when the universe was young, allowing direct tests of model predictions for early cosmic epochs. The James Webb Space Telescope has revolutionized these comparisons by providing unprecedented views of stellar populations in the early universe. Its infrared sensitivity allows observations of highly redshifted galaxies whose light has been stretched to longer wavelengths by cosmic expansion, revealing stellar formation processes operating under the very different physical conditions that prevailed billions of years ago. These observations have revealed that stellar populations in the early universe were often more massive and more actively star-forming than comparable systems in the local universe. The higher gas densities and different chemical compositions of the primordial universe created conditions that favored the formation of extremely massive stars that are rarely seen today. The feedback processes generated by these massive stellar populations profoundly influence the evolution of early galaxies and the broader cosmic environment. Intense stellar winds and supernova explosions could drive galactic-scale outflows that enrich the intergalactic medium with heavy elements, while simultaneously removing gas needed for continued star formation. Understanding these ancient stellar populations and their influence on cosmic evolution is crucial for developing accurate estimates of the total stellar census throughout cosmic history. The stars forming in the early universe represent a significant fraction of all stars ever formed, and their properties may have been systematically different from the stellar populations we observe locally. Machine learning techniques are increasingly being applied to the analysis of large stellar population datasets, allowing astronomers to identify subtle patterns and correlations that would be impossible to detect through traditional methods. These computational approaches are revealing new classes of stellar populations and evolutionary pathways that challenge existing theoretical frameworks. The application of artificial intelligence to stellar population studies is particularly valuable for analyzing the massive datasets produced by modern survey telescopes. Projects like the Gaia mission have measured properties of nearly 2 billion individual stars within our own galaxy, creating datasets too large for traditional analysis methods. Similar challenges arise when analyzing populations of distant galaxies observed in deep extragalactic surveys. The combination of photometric and spectroscopic data for millions of galaxies requires sophisticated statistical techniques to extract meaningful information about their stellar populations and evolutionary histories. The uncertainty inherent in all stellar population measurements must be carefully propagated through any attempt to estimate the total cosmic stellar census. Each observational technique introduces its own systematic errors and selection effects, while theoretical models carry uncertainties related to our incomplete understanding of stellar physics and galactic evolution. Monte Carlo simulations are commonly employed to explore how these various uncertainties combine to affect final estimates of stellar populations. These statistical approaches generate thousands of possible realizations consistent with observational constraints, providing probability distributions for derived quantities rather than single-valued estimates. The results of these uncertainty analyses reveal that current estimates of the total stellar population carry error bars spanning factors of several. While we can be confident that the universe contains at least tens of sextillions of stars, the upper bound could be several times larger depending on assumptions about stellar formation efficiency, the initial mass function, and the total size of the universe beyond our observational horizon. Future observational facilities promise to reduce these uncertainties through more precise measurements of stellar populations across a wider range of cosmic environments and evolutionary stages. The upcoming extremely large telescopes will enable direct observations of individual stars and galaxies throughout the local supercluster, providing unprecedented samples for stellar population studies. Space-based infrared telescopes will peer through cosmic dust to reveal hidden stellar populations in the most obscured regions of star-forming galaxies. These observations are particularly important for understanding stellar formation in the early universe, when dust extinction may have hidden much of the stellar formation activity from optical telescopes. Gravitational wave astronomy offers another complementary approach to studying stellar populations through the detection of merging compact objects. The rates and properties of these gravitational wave sources provide information about the evolution of massive binary star systems over cosmic time, constraining models of stellar formation and evolution in ways that complement traditional electromagnetic observations. The synergy between these diverse observational approaches promises to provide increasingly detailed and accurate pictures of stellar populations throughout cosmic history. Each technique probes different aspects of stellar evolution and different cosmic environments, building a comprehensive view of the stellar universe that no single method could achieve alone. As our understanding of stellar populations continues to evolve, so too will our estimates of the total number of stars in the universe. The numbers we cite today represent our current best estimates based on available observations and theoretical understanding, but they will undoubtedly be refined as new data becomes available and our models improve. What seems unlikely to change is the absolutely staggering scale of the cosmic stellar population and its profound implications for understanding our place in the universe. Whether the final count settles on tens of sextillions or hundreds of sextillions of stars, we are confronting a reality that challenges human comprehension while simultaneously connecting us intimately to the cosmic story. The calcium in your bones was forged in the nuclear furnaces of massive stars that exploded billions of years ago. The iron in your blood was created during the final moments of stellar collapse, when temperatures and pressures exceeded anything found on Earth. The oxygen you breathe was synthesized in stellar cores through nuclear reactions that have been operating throughout cosmic history. This intimate connection between stellar nucleosynthesis and biological evolution means that the cosmic stellar census is not merely an abstract astronomical exercise, but rather a fundamental aspect of understanding how complexity and consciousness emerged from the simple hydrogen and helium that filled the primordial universe. Every breath you take contains atoms that have journeyed through multiple stellar generations, being recycled through the cosmic ecosystem of stellar birth, evolution, and death that has been operating for nearly 14 billion years. The stellar populations we observe throughout the universe represent not just distant lights in the sky, but rather the cosmic factories that created the very elements from which you are made. As you settle deeper into contemplation of these vast stellar populations, remember that their story is your story. The nuclear processes operating in stellar cores throughout the cosmos are the same processes that created the building blocks of your cells, your thoughts, and your capacity for wonder about the universe itself. The quest to count every star in the universe thus becomes a quest to understand the full scope of the cosmic processes that made your existence possible. Each stellar census, each galaxy survey, each measurement of stellar formation rates contributes to a growing understanding of how the universe has evolved from primordial simplicity to the rich complexity that surrounds us today. Through patient observation and careful analysis, astronomers are slowly piecing together the complete story of stellar populations throughout cosmic history. This story encompasses not just the final count of stars, but the entire narrative of how those stars formed, evolved, and contributed to the ongoing cosmic evolution that continues around us at every moment. The numbers we derive from this cosmic accounting may seem impossibly large, but they represent the accumulated result of nearly 14 billion years of stellar formation and evolution. Each star counted in our census represents a unique nuclear furnace that has contributed to the cosmic inventory of heavy elements, the chemical complexity that makes planets and life possible. As you drift towards sleep tonight, carried by the gentle rhythm of your breathing, remember that you are part of this magnificent stellar story. The atoms flowing through your bloodstream, the electrical impulses firing in your neurons, the very thoughts contemplating these cosmic mysteries, all bear the nuclear signature of stellar processes that have been operating since the universe was young. The stellar populations scattered throughout those 2 trillion galaxies continue their ancient dance of formation and evolution, creating new heavy elements and new possibilities for complexity with each passing moment. Through your existence, through your capacity for wonder and understanding, the universe has achieved something truly remarkable: the ability to contemplate its own stellar heritage and marvel at the improbable beauty of its own vast design. In counting the stars, we are really counting the cosmic processes that created everything we know and love about existence itself. The final number, however large it may be, represents not just distant lights, but the fundamental creative forces that have been shaping reality since time began. Forces that continue to operate throughout the universe at this very moment as you rest here under the gentle glow of our own stellar neighbor, contemplating your connection to the infinite stellar community that stretches across all of space and time. The investigation into stellar populations becomes even more intricate when we consider the phenomenon of stellar recycling operating throughout cosmic history. Unlike the linear progression we might imagine, where stars simply form burn and die. The reality involves an elegant cosmic choreography where the death of one stellar generation directly enables the birth of the next. This perpetual cycle of stellar renewal has been operating since the first massive stars exploded over 13 billion years ago, gradually transforming the chemical composition of the universe itself. Picture a massive star nearing the end of its relatively brief but spectacular life. For millions of years, this stellar giant has been fusing lighter elements into heavier ones in its nuclear core, creating a cosmic foundry that operates at temperatures exceeding 100 million degrees. Silicon transforms into iron, carbon becomes neon, oxygen fuses into silicon. Each nuclear reaction adding to the star's growing inventory of heavy elements that were completely absent from the primordial universe. When this massive star finally exhausts its nuclear fuel, the result is one of nature's most spectacular events. The stellar core collapses in mere seconds, rebounding in a supernova explosion that can briefly outshine an entire galaxy containing billions of other stars. But this dramatic death serves a cosmic purpose far beyond mere spectacle. The explosion disperses all those newly created heavy elements throughout the surrounding interstellar medium, enriching vast regions of space with the chemical building blocks necessary for rocky planets and complex chemistry. These enriched gas clouds become the raw material for future stellar generations, creating a cosmic inheritance system where each stellar family passes its nuclear achievements to its descendants. Stars forming today have access to the complete periodic table of elements, enabling the formation of terrestrial worlds and the intricate molecular processes that make biology possible. Your own existence depends entirely on this ancient cycle of stellar death and rebirth that has been operating throughout cosmic history. The efficiency of this stellar recycling process varies dramatically across different cosmic environments. In regions of active star formation, the cycle operates rapidly, with successive generations of stars forming from increasingly enriched material. Dense stellar clusters can experience multiple episodes of enrichment within relatively short cosmic timescales, creating stellar populations with remarkably high concentrations of heavy elements. Conversely, in isolated regions far from active star formation, the recycling process proceeds much more slowly. Ancient stellar populations in these cosmic backwaters may retain chemical compositions that reflect conditions from billions of years ago, serving as fossil records of earlier cosmic epochs. These chemical time capsules provide astronomers with direct insights into stellar formation processes operating under very different conditions than those we observe today. The study of stellar chemical evolution has revealed systematic patterns that reflect the underlying physics of stellar nucleosynthesis and galactic dynamics. Elements lighter than iron are primarily produced through nuclear fusion in stellar cores, with different stellar masses contributing different elements to the cosmic inventory. Elements heavier than iron require even more extreme conditions, typically forming during the explosive final moments of stellar collapse, or in the aftermath of neutron star mergers. These different nucleosynthetic pathways create distinct chemical signatures that can be traced through stellar populations across cosmic time. The relative abundances of different elements in a star's atmosphere serve as a kind of stellar DNA, revealing information about the nuclear processes that created those elements and the environments in which the star formed. Globular clusters, provide particularly valuable laboratories for studying stellar chemical evolution because they contain large populations of stars that formed at approximately the same time from the same initial material. Yet even within these apparently simple stellar systems, astronomers have discovered unexpected chemical complexity that challenges traditional models of stellar formation and evolution. Many globular clusters contain multiple stellar populations with subtly different chemical compositions, suggesting that these systems experienced extended periods of star formation rather than forming all their stars in a single burst. The presence of these chemical variations within globular clusters indicates that stellar recycling processes were operating even within these dense stellar environments, creating successive generations of chemically distinct stellar populations. The implications of these discoveries extend far beyond individual stellar systems to encompass our understanding of galactic chemical evolution as a whole. If even the apparently simple environments of globular clusters can produce chemical complexity through stellar recycling, then the chemical evolution of entire galaxies must be correspondingly more intricate and nuanced. Recent observations of extremely metal-poor stars have pushed the boundaries of stellar archaeology to even greater extremes. These ancient stellar survivors contain chemical compositions that reflect conditions in the very early universe, when only the first few generations of stars had contributed to cosmic chemical enrichment. Their atmospheric compositions provide direct constraints on the masses and explosion energies of the first stars, stellar populations that ceased to exist over 10 billion years ago. The search for the most metal-poor stars has revealed a surprising diversity in early stellar populations and nucleosynthetic processes. Some ancient stars show evidence of enrichment by unusually massive stellar explosions, while others bear the chemical signatures of more typical supernova events. This diversity suggests that the first stellar generations included a wide range of stellar masses and explosion types, creating a complex foundation for subsequent cosmic chemical evolution. Population synthesis models attempt to capture this chemical complexity by tracking the detailed nuclear yields from different types of stellar explosions over cosmic time. These sophisticated simulations must account for the varying contributions from stars of different masses, the time delays between stellar formation and explosion, and the mixing processes that distribute heavy elements throughout galactic environments. The validation of these chemical evolution models requires comparison with observations spanning the full range of stellar metallicities and galactic environments. Local stellar populations provide detailed chemical abundance patterns that constrain nucleosynthetic yields and mixing processes. Distant galaxies offer snapshots of chemical evolution at earlier cosmic epochs, when enrichment levels were lower and different stellar populations dominated. The James Webb Space Telescope has opened new windows into early cosmic chemical evolution by enabling spectroscopic observations of galaxies at unprecedented distances and redshifts. These observations reveal stellar populations forming in environments with chemical compositions dramatically different from anything observed in the local universe, providing direct tests of chemical evolution models in previously inaccessible parameter regimes. Early results from these observations suggest that chemical enrichment in the primordial universe may have proceeded more rapidly than previously expected. Some high redshift galaxies show surprisingly high heavy element abundances for their cosmic age, indicating that stellar recycling processes were operating efficiently even when the universe was less than 1 billion years old. These discoveries have important implications for understanding the total stellar census throughout cosmic history. If chemical enrichment proceeded rapidly in the early universe, it suggests that massive stellar populations were forming and evolving at rates that may have been systematically underestimated in previous cosmic surveys. The chemical evidence thus provides an independent constraint on early stellar formation rates and total stellar populations. The role of stellar feedback in regulating both chemical enrichment and ongoing star formation adds another layer of complexity to stellar population evolution. When massive stars explode as supernovae, they don't just enrich the local environment with heavy elements. They also inject enormous amounts of energy that can heat surrounding gas and drive galactic-scale outflows that remove material from star-forming regions. This feedback process creates a delicate balance between stellar formation and stellar destruction that varies significantly across different galactic environments. In low-mass galaxies, with shallow gravitational potential wells, supernova feedback can be so efficient that it completely halts star formation for extended periods, creating gaps in the stellar formation history that affect total stellar population estimates. Conversely, in massive galaxies with deep potential wells, stellar feedback may be less effective at removing gas, allowing star formation to continue for longer periods and producing larger total stellar populations. The interplay between stellar feedback and galactic mass creates systematic variations in stellar formation efficiency that must be accounted for in any comprehensive census of cosmic stellar populations. Active galactic nuclei powered by supermassive black holes introduce yet another form of feedback that can profoundly influence stellar populations throughout entire galaxies. When material falls into these central black holes, it releases enormous amounts of energy that can heat gas throughout the galactic environment, potentially suppressing star formation on galactic scales. The relationship between black hole activity and stellar populations appears to be closely connected, with periods of intense black hole growth often coinciding with episodes of rapid stellar formation. This connection suggests that the same gas reservoirs that fuel star formation can also feed central black holes, creating a complex interplay between stellar and black hole growth that shapes galactic evolution. Understanding these feedback processes is crucial for developing accurate models of stellar population evolution over cosmic time. The total number of stars that form in any given galaxy depends not just on the initial gas supply, but also on how efficiently feedback processes regulate the conversion of gas into stars throughout the galaxy's evolutionary history. Environmental effects operating on even larger scales add additional complexity to stellar population evolution. Galaxy clusters create unique environments where interactions between galaxies can dramatically alter their stellar formation histories. High-speed encounters can strip gas from galaxies, effectively ending their stellar formation careers and preserving their stellar populations at the moment of gas removal. The hot intracluster medium that permeates galaxy clusters can also remove gas through ram pressure stripping, where the pressure of motion through the hot gas literally blows away a galaxy's star-forming material. These environmental processes create systematic differences in stellar populations between cluster and field galaxies that must be accounted for in cosmic stellar censuses. Tidal interactions between galaxies can trigger intense bursts of star formation, by compressing gas clouds and destabilizing stellar orbits. These interaction-induced starbursts can temporarily increase stellar formation rates by factors of 10 or more, creating brief but intense episodes of stellar birth that contribute disproportionately to total stellar populations. The frequency of galaxy interactions and mergers has evolved dramatically over cosmic time, with interaction rates being much higher in the dense compact universe of earlier epochs. This evolution in interaction rates translates directly into evolution in stellar formation processes, with early cosmic epochs experiencing more frequent merger-driven starbursts than the relatively quiescent universe we observe today. Binary stellar evolution adds yet another dimension to the complexity of stellar population modeling and census efforts. Recent observations suggest that most stars form in binary or multiple systems, where gravitational interactions between stellar companions can dramatically alter their evolutionary paths compared to isolated single stars. Mass transfer between binary companions can rejuvenate aging stars, extend their lifetimes, and create exotic objects that would be impossible in single-star evolution. Some binary systems can experience multiple episodes of mass transfer, creating complex evolutionary sequences that challenge traditional stellar evolution models. The endpoints of binary evolution include some of the most energetic events in the universe, including Type Ia supernovae produced by exploding white dwarf stars and gravitational wave sources created by merging compact objects. These phenomena provide independent traces of stellar populations and evolutionary processes that complement traditional stellar surveys. Gravitational wave astronomy has opened an entirely new window into stellar populations by enabling direct detection of merging stellar mass black holes and neutron stars. The rates and properties of these gravitational wave sources provide information about massive stellar evolution and binary formation processes that occurred billions of years ago. The diversity of gravitational wave sources detected so far suggests that stellar populations contain a rich variety of compact object binaries formed through different evolutionary pathways. Some systems likely formed through isolated binary evolution, while others may have been assembled through dynamical processes in dense stellar environments. The chemical evolution of stellar populations continues to operate today through ongoing stellar formation and evolution processes. Every massive star that explodes as a supernova adds to the cosmic inventory of heavy elements, while every stellar generation that forms incorporates the nuclear legacy of its predecessors into new stellar and planetary systems. This ongoing chemical evolution means that stellar populations forming today have access to higher heavy element abundances than any previous stellar generation. The implications for planetary formation and potentially for the emergence of life are profound, as the availability of heavy elements directly affects the types of worlds that can form around different stellar populations. The discovery of potentially habitable exoplanets around stars with a wide range of chemical compositions has revealed that planet formation can occur under much more diverse conditions than previously expected. This diversity suggests that the cosmic real estate suitable for complex chemistry and potentially life may be much more extensive than early estimates suggested. As stellar populations continue to evolve and enrich the cosmic environment, future generations of stars and planets will have access to even higher concentrations of heavy elements. This ongoing chemical evolution raises fascinating questions about how stellar and planetary properties might continue to evolve over cosmic timescales, far exceeding the current age of the universe. The temporal evolution of stellar populations creates additional challenges for cosmic census efforts, because the stellar population we observe at any given moment represents a snapshot of an ongoing evolutionary process. Stars forming today will contribute to the cosmic stellar population for billions of years into the future, while ancient stellar populations continue to evolve and eventually fade away. Red dwarf stars, the most numerous type of star in the universe, illustrate this temporal complexity particularly well. These small, dim stars burn their nuclear fuel so slowly that they can remain active for trillions of years. This means that virtually every red dwarf that has ever formed is still burning today, since the universe hasn't existed long enough for any red dwarf to reach the end of its natural lifetime. The longevity of red dwarf stars has important implications for the long-term evolution of the cosmic stellar population. While massive stars rapidly cycle through their evolution and contribute to ongoing chemical enrichment, red dwarfs represent a more permanent component of the stellar census that will continue burning long after the current epoch of active star formation has ended. Current models of cosmic evolution suggest that star formation rates throughout the universe have been declining for several billion years as galaxies consume their gas reservoirs and stellar feedback becomes more efficient at preventing new star formation. If these trends continue, the universe may be approaching the end of its primary star-forming epoch. In this scenario, the stellar population we observe today may represent close to the maximum number of stars that will ever exist in the universe. Future cosmic epochs will be dominated by the evolution of existing stellar populations rather than the formation of new stars, gradually shifting the cosmic stellar census toward older, dimmer, and longer-lived stellar types. The prospect of a universe dominated by ancient red dwarf stars burning in slowly fading galaxies provides a poignant backdrop for considering our current cosmic epoch. We may be living during a relatively brief golden age of stellar formation and cosmic activity, surrounded by the vigorous stellar populations that will define the universe's long-term stellar legacy. Yet even as star formation rates decline, the ongoing evolution of existing stellar populations ensures that the cosmic stellar census will continue to change over time, scales vastly exceeding human experience. The interplay between stellar birth, evolution, and death will continue to reshape galactic stellar populations for billions of years to come. Understanding these long-term evolutionary trends requires sophisticated models that can track stellar population evolution over cosmic timescales spanning tens of billions of years. These models must account for the detailed physics of stellar evolution, the chemical enrichment of galactic environments, and the complex feedback processes that regulate star formation rates. The results of these long-term evolution models provide fascinating insights into the ultimate fate of stellar populations throughout the universe. In the far future, when active star formation has ceased and existing stellar populations have aged, the cosmos may become a much quieter and dimmer place, dominated by the fading embers of today's vigorous stellar activity. But that distant future remains billions of years away, and the current epoch continues to offer spectacular displays of stellar formation and evolution throughout the observable universe. The stellar populations we observe today represent the accumulated result of nearly 14 billion years of cosmic evolution, each star a unique participant in the ongoing story of how the universe has transformed from primordial simplicity to the rich complexity that surrounds us. As you contemplate these vast stellar populations scattered throughout space and time, remember that their story encompasses not just distant astronomical objects, but the very processes that created the elements from which you are made. The nuclear fusion operating in stellar cores throughout the universe represents the same fundamental physics that forged the atoms flowing through your bloodstream at this very moment. The cosmic stellar census thus becomes more than an abstract exercise in astronomical accounting. It represents a comprehensive survey of the nuclear processes that have shaped the chemical evolution of the universe and made complex chemistry, rocky planets, and ultimately life itself possible. Every star counted in our cosmic survey represents a unique nuclear furnace that has contributed to this ongoing process of cosmic chemical enrichment. Whether massive and short-lived or small and long-burning, each stellar population participates in the grand cosmic recycling system that has been operating since the first stars ignited in the primordial darkness. Through patient observation and careful analysis, astronomers are slowly assembling a complete picture of how stellar populations have evolved throughout cosmic history and how they continue to shape the universe around us. This ongoing investigation represents humanity's attempt to understand our own cosmic origins and our place in the vast stellar community that extends throughout space and time. The numbers we derive from this cosmic census may seem impossibly large, but they reflect the accumulated result of processes that have been operating since the universe began. Each stellar population, each galactic environment, each episode of stellar formation and evolution contributes to the rich tapestry of cosmic history that connects us intimately to the stars themselves. As you rest here tonight, breathe in slowly and letting your mind drift among these countless stellar populations, remember that you are not merely observing this cosmic story from the outside. You are an active participant in the ongoing evolution of stellar materials that have been cycling through the universe for billions of years, temporarily organized into the remarkable pattern of consciousness that enables you to contemplate your own cosmic heritage. The stellar populations burning throughout those 2 trillion galaxies continue their ancient dance of nuclear transformation, creating new possibilities for complexity and consciousness with each passing moment. Through your existence, through your capacity for wonder and understanding, the universe has found a way to appreciate its own stellar magnificence and marvel at the improbable beauty of its own vast and intricate design. The profound realization that stellar populations are not evenly scattered throughout the cosmos, but follow intricate patterns shaped by the universe's largest structures, adds yet another layer to our impossible counting task. When we map the distribution of galaxies across vast distances, we discover that they trace out what astronomers call the cosmic web, a 3-dimensional tapestry of filaments and voids that spans billions of light years. Picture soap bubbles clustering together in a sink full of foam. The galaxies, with their countless stellar inhabitants, concentrate along the thin films where these cosmic bubbles meet, while enormous empty regions stretch between them, like the hollow interiors of the bubbles themselves. This isn't a random arrangement, but rather the natural result of how matter has been pulled together by gravity. over nearly 14 billion years of cosmic evolution. Within the dense filaments of this cosmic web, where thousands of galaxies cluster together, stellar interactions become far more frequent and dramatic than anything we observe in isolated regions. High-speed encounters between entire galactic systems can trigger spectacular bursts of new star formation as gas clouds collide and compress. These cosmic traffic accidents can increase stellar birth rates by factors of hundreds, temporarily flooding local regions with newborn stars. The environmental pressures within these crowded cosmic neighborhoods also accelerate stellar death rates through processes that would be impossible in quieter regions. Stars that might otherwise burn peacefully for billions of years find themselves torn apart by tidal forces or consumed in stellar collisions that create exotic objects, unlike anything found in our galactic suburbs. At the opposite extreme, in the vast cosmic voids that separate these stellar metropolises, space becomes so empty that individual galaxies drift in almost perfect isolation. A galaxy residing in one of these cosmic deserts might not encounter another stellar system for hundreds of millions of years. Their stellar populations evolve in cosmic solitude, following evolutionary paths determined purely by internal processes rather than external influences. Recent deep field observations have revealed something unexpected about these supposedly empty regions. Faint streams of ancient starlight have been detected stretching across the cosmic voids, suggesting the presence of vagrant stellar populations that were ejected from their parent galaxies billions of years ago. These cosmic wanderers now drift through the darkness between galaxy clusters, their light so dim it can barely be detected by our most sensitive instruments. These discoveries force us to reconsider what we mean when we attempt to count every star in the universe. Are we counting only the stars currently residing within organized galactic structures? Or should we include these homeless stellar populations that have been cast out into the cosmic wilderness? Each approach yields dramatically different totals, highlighting how the very definition of our cosmic census affects the final numbers. The temporal dimension adds yet another layer of complexity to our counting efforts. When we observe the most distant galaxies visible to our telescopes, we're seeing them as they existed when the universe was just a fraction of its current age. The light from these ancient stellar populations has been traveling toward us for over 13 billion years, carrying information about cosmic conditions that no longer exist anywhere in the observable universe. This means our cosmic stellar census is really a survey spanning nearly the entire history of the universe. The nearby galaxies show us stellar populations as they exist today, shaped by billions of years of evolution and environmental influences. The most distant galaxies reveal stellar formation processes operating under the very different conditions that prevailed when the cosmos was young, dense, and chemically primitive. Bridging these temporal extremes requires sophisticated models that can account for how stellar formation rates, galaxy properties, and environmental conditions have evolved over cosmic time. The stellar populations forming in the early universe operated under physical conditions so different from today that they might as well have been governed by entirely different laws of physics. In those ancient epochs, the universe was smaller, denser, and hotter than it is now. Gas clouds that would eventually become galaxies were being compressed by the overall cosmic expansion, while simultaneously collapsing under their own gravity. The interplay between these competing processes created conditions that could trigger stellar formation at rates far exceeding anything we observe in the modern universe. Some early galaxies were forming new stars at rates hundreds of times faster than our own Milky Way, creating stellar populations so massive and luminous that individual galaxies could outshine entire clusters of modern galaxies. These cosmic furnaces burned through their available gas reservoirs in just a few 100 million years, creating brief but incredibly intense episodes of stellar birth that contributed disproportionately to the total cosmic stellar census. The chemical environment of these early stellar populations was also radically different from anything we observe today. The universe had not yet been enriched with heavy elements produced by previous stellar generations, so these ancient stars formed from gas containing almost exclusively hydrogen and helium. Their nuclear evolution proceeded differently than modern stars, potentially creating stellar types and explosion patterns that no longer exist in the contemporary universe. Understanding these primordial stellar populations is crucial for developing accurate estimates of the total cosmic stellar census. If early stellar formation rates were systematically higher than current observations suggest, then our total stellar counts could be significant underestimates. Conversely, if early stellar populations were dominated by very massive stars that burned out quickly, then their contribution to the long-term stellar census might be smaller than their dramatic formation rates would suggest. The challenge of accounting for stellar death over cosmic timescales adds another dimension to our counting difficulties. Every second throughout the universe, new stars are being born, while others reach the ends of their evolutionary lifespans. This cosmic cycle of stellar birth and death has been operating for nearly 14 billion years, constantly reshaping the stellar populations we observe. Massive stars live fast and die young, exploding as supernovae after just a few million years of nuclear burning. These stellar giants contribute dramatically to cosmic chemical enrichment, but their brief lifespans mean that most of the massive stars that have ever existed are no longer contributing to the active stellar census. Their deaths have left behind exotic remnants, like neutron stars and black holes that still contain stellar mass but no longer shine with nuclear fire. Medium-mass stars like our Sun burn more conservatively, potentially remaining active for tens of billions of years. Many of these stars that formed in the early universe are still burning today, contributing to both ancient and modern stellar populations. Their longevity makes them important contributors to the total cosmic stellar mass, even though they're individually much less luminous than their massive cousins. The smallest stars, the red dwarfs, burn their nuclear fuel so slowly that they can remain active for trillions of years. Since the universe is only about 14 billion years old, virtually every red dwarf that has ever formed is still burning today. These tiny stellar survivors represent the most numerous component of the cosmic stellar population, yet they're so faint that they can only be detected in our immediate galactic neighborhood. This diversity in stellar lifetimes creates a complex temporal structure in the cosmic stellar census. The stellar population we observe at any given moment represents a mixture of different stellar generations, each contributing according to their formation rates and evolutionary timescales. Ancient stellar populations continue to evolve and fade, while new stellar generations add to the total count with each passing moment. Binary star systems add yet another layer of complexity to both stellar evolution and cosmic census efforts. Recent surveys suggest that most stars don't exist in isolation like our Sun, but are born as part of gravitationally bound multiple systems. These stellar partnerships can profoundly alter each star's evolutionary path through gravitational interactions and mass transfer processes. Close binary systems can experience episodes where material flows from one star to its companion, rejuvenating aging stars and creating exotic objects that would be impossible in single-star evolution. Some systems undergo multiple episodes of mass exchange, creating complex evolutionary sequences that can extend stellar lifetimes far beyond what single-star models would predict. The most dramatic binary interactions result in stellar mergers or explosive events that can briefly outshine entire galaxies. Type Ia supernovae, produced when white dwarf stars in binary systems accumulate enough material to trigger explosive nuclear burning, serve as cosmic standard candles that allow astronomers to measure distances across the universe. These events represent the ultimate endpoint of binary evolution, while simultaneously providing tools for studying stellar populations in distant galaxies. When we scale these complex binary interactions up to cosmic dimensions, accounting for the billions of binary systems in each galaxy and the trillions of galaxies throughout the observable universe, the challenge of maintaining an accurate stellar census becomes almost overwhelming. Every stellar interaction, every mass transfer episode, every merger event potentially changes the total count in ways that are difficult to predict or observe directly. The discovery of gravitational waves has opened an entirely new window into these stellar population dynamics by enabling direct detection of merging compact objects. When two stellar mass black holes or neutron stars spiral together and merge, they create ripples in space-time itself that carry information about stellar populations that existed billions of years ago. And so, we reach the end of our impossible journey through the cosmic stellar census. Having traced the universe's stellar heritage from the first primordial giants to the countless red dwarfs that will burn long after our sun has faded to darkness. Whether the final count settles on 70 billion trillion stars, or 200 sextillion, or some even more incomprehensible number, we've discovered something far more profound than mere mathematics. We've glimpsed the intricate cosmic machinery that transforms hydrogen and helium into gold and carbon, gravity and time into consciousness and wonder. Every star we've contemplated tonight burns with the same nuclear fire that forged the atoms flowing through your bloodstream, making you not just an observer of this stellar multitude, but an active participant in the ongoing cosmic story. As you drift towards sleep, remember that you are the universe's way of counting itself, a temporary but magnificent arrangement of stellar materials that has achieved the extraordinary feat of cosmic self-awareness. Sweet dreams, fellow stargazer, knowing you rest under the gentle light of our own stellar neighbor, forever connected to the infinite stellar community that dances throughout all of space and time.